All right, and I was mentioning we'll go through section 18, which is a beast of a section. All really great information. I will put a little caveat for section 18. First of all, a quick thumbs up. People have touched section 18. Look at that. Okay, cool. All right, somewhat. All right, awesome. Section 18, I'll say there's a whole bunch of discussion on different distributions, like the Bernoulli distribution, Poisson distribution, what else? Binomial. There's a whole bunch of those parts, and I think that also talks about in the curriculum the different averages and standard deviations. Note that those are things I personally think you don't have to memorize. There aren't things that you need to say, oh, I need to memorize this, otherwise I'm not a real data scientist or something like that. The important part is really recognizing where these distributions come from and knowing what situations they might arise from. So that way you're like, oh, I would expect a Poisson distribution in this situation, or, oh, I would use a Poisson distribution and use those metrics for the situation. And honestly, that takes some time and stuff like that. But it's good to know what they are and how to look them up versus just trying to memorize essentially, what are these distributions. Cool. All right, I just wanted to give that little caveat since going through. And like I mentioned before, we might not go through all parts of section 18. We might leave that for tomorrow. So just kind of be aware of that. Cool. All right, so let me go ahead and start sharing my screen. But I guess while I'm getting that set up, anyone have any questions they wanted to ask right off the bat? Okay, cool. All right, so now I shared my screen. And let me just resize it so it's a little bit easier for us to read. Okay, so sorry, I have a few of these up here. I don't know why I'm going through. So again, you can find these notebooks in the repo, right, that I usually have and all that stuff. Oops. And so let's go right into it. So note that there's our typical imports that we have, Pandas, Seaborn. I'm just importing this for later. SciPy stats, know that we're going to look at a little bit something on skew norm. I will talk a little bit about that. I don't actually know if I use this specifically in this notebook, but just know these are just the common imports we usually have. Okay, so first thing to know before we talk about any distributions, kind of related to when we talked about last time with probability, is randomness, right? And so if you're familiar with computer science, you might be familiar with the idea of pseudo-random numbers. But if you're not, basically computers can't be random, not in the way that we think of randomness, is that computers have to be deterministic. If this goes in, this comes out. And there's some ways you can kind of get around this and stuff like this, but sometimes we need random numbers. Sometimes we randomly generate a number, or, I want this specific, I want a random part in this list or something like that. It's well, computers can't be random, so how do we get random numbers? Essentially, we fake it with a pseudo-random number. And basically, I'm not going into too much detail, but basically there's a complicated function that looks random and it has certain properties to make it seem random. But the thing is, what we can do is we can give it what we call a seed. And so the seed basically is where it starts off at, where that function starts off, and then it's deterministic. So given a seed, you will always get the same answer going forward. So this is where you'll see when we do import NumPy, if we're using the random package of NumPy, that seed, I just gave it number 27, just because I gave it just that number. This is saying, okay, start here. I'm sorry? What's that?
Does it matter what number you give it?
I mean, it matters in the sense that there's a different number, it's a specific one. So for example, we'll check this out, right? So I'll do import random seed. So that means it's starting from this specific point in the complicated function that will produce random numbers or pseudo-random numbers. And this will basically pick a random integer, right, between 1 and 10, pick 5 of them. Is that right? That should be right, yeah. So you can see 8, 6, 2, 9, 8, right? If I run this again, you'll get more random stuff, right? If, however, let's see if I can just copy this. We'll keep these down here. And let's say I give a new number, let's say 42, right? Well, this will give new random numbers. See that? But now if I change this back to number 4, rerun this, and now I'm seeding it over, this will reproduce the same numbers that we saw before. Oh, oops, I deleted one. It was started with an 8, and then I think, was it 3 something? Oh, 8, 6, I think that was it. But the second one will be this exact thing. And you can see that. So this is the way, the reason why we do this seed here too is that we can have consistency. So it is random, but we're doing the same random numbers, if that makes sense. It makes it a little bit easier for us to test versus saying hey, is this actually a random number? Is this some bug in my code, or is this just coming out as just part of the randomness is in there? This helps it make it a little more consistent and easier to figure that out.
Is there like a best practice to decide what number to have in your seed?
No, not really. You'll see a lot of 42s, for example, because people think they're hilarious, I guess. But like, no, like people just have their whatever favorite number they have, they'll just do that number. One thing to note is that if anyone does any Kaggle competitions, you'll notice that people will use a certain seed, and sometimes the seed will, like, just by chance, will perform better than other seeds. That's not really a good way to like approach it, because then it's like, oh, you're just picking the right random numbers to make your model better. So just kind of think of like your seed just being so you're consistent, so you can compare to make sure that you're not rerunning it over and over again. It's like, well, you know, you can judge on the algorithm itself. Okay, so little segue that I don't think the curriculum mentions specifically, but it's an important aspect of, I think, when we're approaching these like distributions and probability, and then later on when we do anything with stochastic, you know, approach. Okay, cool. So I'll move on now to the actual distribution stuff, right? So let's go to showing distributions. So here, just kind of did a quick thing. I basically am writing, I think I did this last time too. Okay, so I have mu, which is going to be our average, usually sigma, right, which is going to be our standard deviation. So I just picked 14 and 2.8. And the number is 5,000. So that'd be 5,000 different numbers. And so I'm actually going to print this out so you guys can see this. Is that if I do this right here, I can get a bunch of random numbers where the mean should be 14 and the standard deviation should be 2.8. So, and I just have 5,000 of them. So for example, if I do, let's do dot size, you can see there's 5,000, right? And you can see if I do, let's say, dot mean, you can see the mean is about 14, right? And then standard deviation, it's about 2.8. So you can see, like, I can basically produce random numbers with these certain properties and stuff like that, okay? We can also read numbers from a data set, right? So we've seen before we can read a data set in, and I'll just go ahead and, let's see there, data.head. Right, so I'm reading that data set, oops, not data, df. You can see here, basically it's a data set. We can see, for example, like a dot describe, but the main thing I think we're going to think about is just the actual, the house median age. So we'll be looking at this as our like numbers or array. But if I look at how many there's 3,000 in here. You can see the mean is 28.84, standard deviation is 12.5, right? I can pull this out directly where I have, for example, our distribution in this case will be the median age, right? Which is just all of this, well, the values, right? And I can calculate the mean from here and the standard deviation. And so if I were to, like, for example, print mu and sigma, to run this now, we can see that these should match up right here. So you can see that part. Okay, makes sense. So these are just two ways we can get data, whether it's from a data file itself, getting a specific column, right? We can check out the distribution, or of course we can actually generate data as well, right? Using something like this, where in this case, I'm making actually a normal distribution where the mean is 14, okay? Cool. And then you can see here for this housing data, we can actually kind of plot this out. And this is kind of like what we'll overall end up doing, is that in this case, I'm actually showing the distribution. So you can see essentially a histogram. You can see this blue curve right here essentially is kind of like a way to like estimate, to like smooth out, say like, well, okay, what if we had something between, like we might not actually have value that is like 21.2 years old for the median age, okay? But maybe we want to actually know what that value is. Well, we can actually create this nice little curve right here to help us extrapolate. So for example, if we don't have any houses that are, let's say, over 50 years old, we can say, well, okay, based on our distribution, you know, we can say, we'll approach it to say like, it would be like about right here. So maybe like only, what's that, about 6% of the houses would be at like 55 years old, okay? Cool. And then you can see this green and this red line in this case. So this line in the middle here essentially is that median age. And then I did mu plus sigma, right? Which will create a line right here. It's one standard deviation away from the mean, and then one standard deviation below the mean. Okay, so you can see that within that point. This again is actually real data, right? We could also have done the same thing with our data up here, which we created. And this is a normal distribution, so you would expect it to look normal. So you can see It looks approximately normal. It is random, so it's not going to be perfectly normal. And in fact, you can see this blue line looks almost like a normal curve, like a Gaussian, right? But you can look at it very carefully. There's some deviations that you can see. There's a little bit of a bump right here, and that blue estimation curve, which we'll actually call, look at it, it's called a KDE. But we'll talk about this in a second. But you can see there's a little bump going off on top of here. And you can also see the mean and then the standard deviations from the mean. Okay, any questions? Cool, pretty understandable so far? Yeah, nothing new, right? Cool. And these lines can be useful, especially if you're drawing out, like you want to specify this specific value, or especially if you want to show where the mean is in a visualization. All right, cool. So now we can actually say, okay, what are the different standard statistical distributions? So we're going to talk about a whole bunch of them, right? So ways to visualize the same information. There's going to be a PMF, probability mass function, cumulative distribution function, CDF, a PDF, probability density function. We'll see how these differ from each other. And then we'll talk about the normal distribution, which is kind of like our holy grail of just like, oh yes, we love normal distribution. We want the normal distributions and everything. Even if things are not normal, we'll say they're normal anyway, because we just love the normal distribution so much. So just kind of like know that this is going to be a very big part. But yeah, and then statistical testing, I think we're actually going to leave that until a little bit later, because I think in section 19 or 20 is that's actually when we'll talk about it. So I'll leave that to tomorrow. Okay, cool. So probability mass function. So probability mass function, I like to think of it as like a histogram. Essentially, it's just saying like what the frequency of these different values are. You can think of it probability mass function. It's like masses hanging on a bar. So sorry, past Victor doesn't know how to spell. There we go. Okay, so you can imagine like hanging from a bar. So that's essentially like, and the heavier it is, it's like the more, like it pull it down. That's kind of like the way I envision it. You can also think of it like a mass, like if you think of like in physics, I guess, like it has a certain inertia if you were to spin it. I don't know. I don't know if that's the best phrasing if I call it the mass function, but that's the idea here. So a good visualization, I think this is directly from the curriculum. I don't know if this looks familiar to you guys who've seen the curriculum already, but essentially this is also called like a stem leaf plot, or is that right? I think usually we refer to this like a stem leaf plot, probability mass function, a PMF. And essentially what's happening here is just saying what the frequency is for each one of these values. So this is very useful when it's much more like category, or like if there's only like, oh, it's either a 6, like a 1, a 2, a 3, or a 4, or a 5, and like nothing else. There's no in-between values. So this makes it really clear. It's like, oh, these are specific points. Okay, so a good way to show this is just, let's go see some code, right? So there's a lot going on in this part, but no, that's not too bad. So note that we're just importing some, some libraries here. Most of it's matplotlib. I'm also importing these collections just to help us make more counting, make counting a little bit easier. You don't necessarily need it, but it does help us out a little bit. And then this matplotlib inline, just remember that allows us to actually plot nice little graphs within this without any funkiness, essentially. So does anyone remember what these percent signs, when we have this percent and then some command in Jupyter?
Is that called a magic command?
That's right. Yeah, it's Jupyter Magic. So if you want to if you see something like this, you're like, oh, what are different magic commands? You can search it that way. Okay. Other than just typing in Jupyter Notebook percent sign, so that kind of helps. All right. So we'll actually create some little simulation here, right? Or yeah. So this case, we're going to roll 2 different dice, right? So we'll have die 1 and die 2. We'll go from 1 to 6. So note that I put 7 because it's not inclusive, right? So only 1 to 6. It is an integer, so I'm not going to have any in between. And in this case, I'm going to roll it 3,000 times. Okay. Then I'm going to roll another die 2 times. And then I'm going to actually calculate a new part, which is a sum of dice, right? So this will actually be the 2 numbers added together. So just know that that would be like the first, if this is an array, this would be an array of 3,000 long of each roll of the die. And then the sum of dice here will basically be the first 2 values added together, this next 2 values added together, and so on. Note that this assumes that they're independent from each other. So like I could have done this in a lot of different ways, but I'm essentially like rolling 2 different dice. I'm essentially rolling a die, 3,000 times, recording it, and then I roll my second die 3,000 times, and I use that as like my 2 dice. I could have technically rolled them together, but they're essentially the same since they're independent. Make sense? Cool. All right. So if I roll this right here, just to kind of show you what this looks like, right? You can see the different values here, all that stuff, right? And just, I guess I should put the sum of dice too, which will now be different numbers. That's okay. But you can see here, these are sums, which should range from what, 2 to 12, right? 2 being the smallest, 12 being the largest. All right, so just kind of good quick check, right? So now what we're gonna do, we're gonna use collections here. Oops. Let's get rid of that. Yeah, whatever, okay. So we're gonna actually count out how many times each number occurs. So note that this counter object right here will actually count on each die, say, okay, how many times does 1 occur, 2 occur, 3 occur, 4 occur, and so on, okay? And then same thing for our sum of dice as well. So if we do this, what would we expect 1, 2, and 3? Is there gonna be any one that's more common than the other? Yeah, not really, right? There might be by chance, like one might be a little more common, but you know, by probability, it's going to be about equal, and at least not really like clear, unless we're like super lucky or something like that. Okay, so if we do this here, we can actually check this out, and we can see here all different numbers. So for example, these are the list of events. I looked at specifically just the sum of dice. You can see here, here's all the events, 3,000 of them. But now we have this counter, which is basically a dictionary. And so it's saying 7 occurs 491 times, 8 occurs 434 times, and so on. So this will have a different distribution and equally, what's it called? It's not going to be equal in that case because we're looking at the sum, right? That hopefully makes sense. It's easier to get a 7 than it is to get a 2, right? And one thing to note too is that this won't include if I only roll it, let's say 3 times, right? There's only 3 different events. Well, it's only going to count 4, 9, 3. It's not going to count, you know, implicitly 12 never occurs, 8 never occurs, and so on. Okay, so just kind of keep that in mind. In this case, though, 3,000 rolls, we probably occurred every single type of event multiple times. Okay, but there's a chance there isn't. So now we're actually going to plot this range. So, oh, sorry. So now we're going to get ready to plot it. So now what we're doing right here is just kind of prepping the data. So note that this range right here, this is just saying like the number is going from 1 to 12, right? So essentially I'm just making a number so we can actually plot out 1 to 12 on our graph. And then our PMF die 2, PMF sum. So what we're doing here is getting the frequency. So all we're essentially doing is like for our PMF die 1, this guy is saying, okay, how many times does this K occur? So let's say, how many times does 1 occur? And we are getting a percentage. In this case, we're dividing it by len of the roll of dice, should be divided by 3,000. So if, let's say 1 occurred, you know, 500 times, right? That would be about 1/6, right? And then note that we're rounding it to a decimal. So this round function is encompassing this whole number, which is a float, okay? And we're just rounding it to 2 decimal points, okay? And then for K in plot range, just remember that K is gonna represent, you know, essentially either 1, 2, 3, 4, 5, all that stuff. Note that I do a .get instead of just using a brace. Does anyone seen .get from a dictionary before? Does anyone remember what that is?
I'm totally guessing.
Mm-hmm.
But didn't we use that for like get keys and get values? Or is that a different thing?
You're close. You're thinking a little bit different. So let me make a quick dictionary here, right? So let's do, I'm gonna do something similar. So 1 occurs like 10 times, 2 occurs like, I don't know, 5 times. Let's say 3 occurs 8 times, right? So I'm just making a dictionary here. You're thinking, Robbie, I think you said like keys, right? So, oops, keys. So that's probably like what you were thinking. It's like, oh, we can get the keys. We can get things like items, right? We can get those parts like pairs, 110, stuff like this. But that's not quite what's going on here with this .get. So what if I wanted to get the value for this part right here? So how many times 2 occurs? How would I write that for getting that from a dictionary?
Would you do like A and then the bracket 2?
2, right? And that should give me the number 5, right? Yeah. Okay. What happens if I wanted to get 3? I put 3 here, right? Oops. Come on. There we go. Okay, so we get 3 here. What happens if I put the number 5, or let's put the number 10, right? So 10 is not one of the keys in here, right? So what would happen here?
It gives you an error.
It gives me an error, right? So that's not good. So 10 occurs 0 times in this, but you can see it's like, well, it doesn't know what 10 is. So what .get does, .get allows us to essentially say, okay, get the value, and if it doesn't exist, return a 0. So if 10 doesn't exist, which normally would give us an error, we can say, all right, just return 0. And you can see here, that gives me 0 here. If I put 2 here, 2 will actually print out 5. This will actually print out 5 since 2 does exist in that dictionary. Okay, it's just basically saying here's the default if it doesn't exist. Okay, and that's really useful in this case. And here I probably could get away with not using it because if I have 3,000 times I roll a die, every time it's probably going to occur, right? But there's one kind of caveat is that I'm doing the plot range from 1 to 12. Well, I know for a fact, like for example, the sum, 1 is never going to occur, right? So I'm actually doing this .get to make sure I just return 0. And then for these die rolls, I'm doing this actually over 12 so I can plot it on the same graph. So it's a little bit easier for us to read. Well, 7, 8, 9, 10, 11, 12 never occur when I just roll one die, right? You can't roll one die and get a 12. So that's why I'm using this .get 0. Okay, cool. Does that make sense to everyone? Okay, so I just wanted to show this part because it's really useful.
So .get works for the keys. It's saying like, look at the keys and see if this key exists, basically. And if not, return whatever arbitrary value I give, usually 0.
Yeah, so I could do something like that. Like, well, none doesn't print out anything, but yeah. So there you go. Good. Yeah, it's just a safer way to get the value from a dictionary. Okay, cool. All right, so I'll go ahead and move on. I wanted to point that out since that is kind of a lot going on in this one part. So I run this guy now. So now no errors, awesome. And now I have these list comprehensions, right? So this is list comprehension. So I have a list now of all the times it occurs, but now it's frequency. So if I were to go ahead and just print this out real quick for PMF die, oops. You can see here, these are the percents where this is going to be when 1 occurs, when 2 occurs, when 3 occurs. And you can see it's about equal except for the times it can never happen, right? So now we can actually take this data, right? And we can print it out, or sorry, plot it out. So you can see I use the plot range, which is going to be 1 to 12, PMF die 1, PFM die 2. I just did this 2 times so you can see it. I'm using a little different 538 because I think that was what the curriculum used just to make it a little more familiar, but you can change the theme. That's not really super important. What you can see here is that this is showing us how often each one occurs. So this is about a little under 18% of the time, right? That 1 occurs, 2 occurs about, 16% of the time and so on. And you can see there's a little bit difference between the 2 different dies, right? So you can see in here, 1 is the most common, just barely. But over here, looks like 4 is the most common, but it's about equal, right? Cool. So then we can actually do this part right here. We can do the same thing with a stem plot. And just to show you the difference between a stem plot and a histogram, you can see here's our stem plot, right, of how often each part occurs, which makes sense, hopefully, is that you would expect it to be kind of this distribution. 7 is the most common one to get. There's so many different ways you can make 7, but you can only build 2 one way, and then 12 only one way, 6 and 6, or 1 and 1. Okay, and you can see here here's the histogram. And it actually has the same exact shape. The difference here, though, this one actually kind of looks kind of funky, right? Because it looks like I need to probably do this. Yeah. Oh, whatever, that's fine. Okay, so we're moving on. So you can see basically it's essentially the same shape here. The difference, though, is that the histogram shows how many those occur, and this one's showing you the probability, or essentially like percent that's occurring here. So note that essentially I could like move that same thing and it'd be like the same like graph, but we call this our probability mass function, essentially showing the frequency versus I guess like the percent frequency. Okay, cool. Any questions on any of these graphs that I showed for PMF? Pretty good. Thumbs up sounds pretty good. Sideways if you're like, I'm a little confused. All right, cool. So there was some quick thumbs up, so I'm happy. All right, so our CDF is another way to display the same data. So a CDF, I think, sometimes can be a little bit confusing. It's a cumulative distribution function. So cumulative means that we just add up everything up. So this is like the function. I don't like writing functions by themselves because sometimes it's a little bit like, wait, what's going on? I think of like, what's it called? Like little equations are like little poetry, but sometimes it's really hard to understand poetry. So sometimes it's good to understand what we're trying to say and then look at how we can shorten it down. Okay, so this function basically is going to represent saying we're just going to add up everything off this side. So if we're plotting the number 1, we just say how many times does 1 occur, right? And then, or I should say percent of times 1 occurs. Then if we plot 2, well, I guess that's 2. Sorry, if we plot 3 now, 3 would basically say, okay, not just plotting how many times 3 occurs, but also 3 plus 2. So basically this would be a little bit higher up. And then 4, it's like, okay, not just 4, but how many times does 4 occur, 3 occur, 2 occur, 1 occur, and going all the way to the side. If I go all the way off to 12, what value would 12 have, considering its probability mass function? 1, right? Basically, you counted it for all the different parts. So you can see that this graph will continuously increase, right? It's accumulating. It's a cumulative distribution function. And that's what this is saying. It's saying, okay, for some number x, in this case, let's say the number 3, right? Consider the probability that x is less than or equal to that number. So that means not just 3, but 2 and 1. So you would add up all those parts, and that would give you the value for that specific x. Okay, so if I read this now, you can see this is the same exact data for that cumulative sum for the summing the 2 dice together. And you can see this continuously stepping up, right? So basically 1 never occurs, so it's 0. And then it steps up to 2. And then 3, 4, 5, 6. Note that these steps are much larger, right, than these like beginning and end steps. Okay, and that's because this occurs more often, right? 6 occurs a lot more often than 2. So that's why there's a bigger jump over here. And that's essentially representing that there's a bigger step this way. Note that it's kind of at this little S shape. So if I were to draw on top of this, with the color that you can see, it kind of has more of an SC shape, right? So you can kind of see this general, like if I connect these little dots, I didn't do a great job, but like if I connected like the little points right here, it would move kind of in this S shape. If I had, I'll keep that up there. If I instead did a PMF of die 1, remember, had about equal, right? So the steps should all be about equal in this case. So you can see it's much more going up and up. In this case, it's going to 12. So if I did this too, let's say, I'm sorry, going, yeah. Oh, didn't, oh, because I only have 12, sorry. Oh, it isn't like that, I forgot. Okay, that's all right. I was trying to show you guys just the segment. Here. There we go. But anyway, it stops at this part. But you can see the steps are all equally spaced, right? So CDF basically will have like a normal distribution will kind of look more and more SE-like. Okay. If you had a sudden jump in there, you might have some bump over everything. So this will be looking more like if I draw a quick line on top of this. Well, if I try to connect these points more or less are in like a straight line. Okay, makes sense? Cool. All right, and we'll see a comparison of all 3 of these in a bit. All right, so moving on to our PDF, our probability density function, right? So our probability density function, note that we said a cumulative distribution function, probability mass function. Our probability density function is basically when we say think of density as being like it's filled out, right? So right now we have like big gaps between 2 and 3, right? You can't get a 2.3, you can't get a 2.2. But sometimes it makes sense for us to consider values that we haven't gotten. For example, if you are measuring someone's weight, for example, right? Well, you might have only measured 122 and like 135, but there are values between those points. So we'd actually want to be able to fill it out and say, well, what's the probability of going between here? In this case, if we just looked at that, we basically would have to say it's the same probability going all the way through. So we like to kind of extend it outward to be a little more smoother, a little more realistic, right? So think of PMFs as like a PDF as like continuous PMF. So here's, again, it's not my image, but I gave a good example, is that this essentially is a PMF. Note that is a PMF because it is this value right here. It's probability, right? It's not count. But on the side here is that you can see this blue line. This blue line is representing the PDF. And then right here in this red, this histogram, imagine it's just like a little point, right? Like we had with the stem. This is our PMF right here. And so we can see that kind of distribution going forward. And this is more or less what we're going to try to grow. Now this, honestly, this PDF is probably not the best way to do it. You can probably see is that it looks way too smooth compared to how the data is. Like if you were to draw out your own, like, let's say your own PMF, you might draw it something like, oops, use my drawing tool, there we go. it might do something like closer to something like this. Right? So you might have something like that, but it's got the general shape. The idea is that we're extrapolating between not just a single point, but points between. Okay, makes sense to everyone so far? Okay, cool. So then it comes down to like, okay, how do we build these things, right? So there's a kind of subtlety to this part, is that before we could just say if there's just like, you know, back here is like just what's the probability of 2 happening? We can actually give that exact value, right, of at least from the data. But if we wanted to give an exact value for a specific point on a PDF, it gets a little more subtle. So a quick like probability question for you guys. It's a little bit of a trick question, but what's the probability of me hitting exactly, like, let's say if I wanted to hit on the right side, right? So like anything on this right side, what's the probability of hitting this target, assuming I'm random? So I throw a dart.
50%.
50%, right? Yeah, okay. 50% of the time I'll hit it right here, 50% I'll hit the other side, right? Easy, okay. What is the probability of me hitting exactly right here? And trying to mention like it dots, infinitely small, infinitesimally small.
Doesn't really exist, right?
Yeah, so it's kind of like we say it's the probability of 0. And sometimes people go like, wait, what? Like how, like, wait, what do you mean probability of 0? Like hitting, like not just that point, but hitting any single point has a probability of exactly 0. And the reason why you can kind of say this, like from a physical standpoint, is like, okay, we throw like a really like thin arrow at this. You're like, oh, I hit it. It's like, well, if I zoom in really far, you didn't quite hit it. You hit a little bit off to the right. It's like, well, no, like I did really well. It's like, okay, we keep zooming in, and basically, well, you're slightly off. We can never get exactly that point, right? So that's essentially where that probability 0 comes from. If you're from physics, you would say infinitesimally small. We love those words in physics, right? But the point here is that we can't say any given point will give you a certain probability. We always have to do a range. So we could do something like a very small circle and say, what's the probability of hitting that small little circle? And that will give us a probability. So just kind of be aware is that we need to actually use a range versus actually saying one specific point. So when we talk about like our PDF here, is that we need to not just consider just like one little point on here, what's the probability of hitting this exact number, but hitting within this range on that part. Okay, cool. I just wanted to make that little note because it is an important aspect. Okay, and so one thing we can do, we can actually normalize our PDF so the area is always 1. Why would we want the area to be 1? I say area, the area underneath this curve. If I were to like color this in.
All the probabilities should add up to 1. So
That's right.
if the area is 1, then it's kind of like it's a 1-to-1.
Yeah. So you want to actually say like, okay, if I go from the range of all possibilities from like 0 to like, let's say the possibilities like 10,000, right? Well, I want that PDF now to encompass like, if I add up all the possible events, right, it will be 1. Basically, that's our probability. So our probability is actually going to be the area underneath the curve itself. Okay. So you can see here is a little graphic, is that this, in this case, is a PDF. This case looks kind of like a normal curve, maybe it's slightly not normal, but basically we just calculate the probability underneath this. Now, normally, you know, you would use calculus or whatever for your like nice, beautiful curve, but we have packages in like computers where we can basically do it for ourselves. But essentially we're saying between 12 and 14, calculate that area underneath, and that will be 0.136 in this case. In that case, 13.6% is the probability of hitting between 12 and 14. Okay. So that is how you get the probability from PDF. And that's usually, you will generally see PDFs over any PMF and stuff like that, unless it's a category or something like that. Okay, so it kind of showed a quick example of all 3. It says histogram. I didn't make this graph, but this histogram, you can think of it much more like a PMF, right? Because it's showing the frequency here in percent. And so you can imagine that this histogram right here is our, what's it called, our PMF in pink. And then this blue right here is actually our CDF, saying basically how it increases over, right? Okay, our different steps. And note that the steps will be really, really small now because we have a lot more different options. And then our PDF here is basically trying to fit a nice smooth curve that goes between, you know, each of these individual points. Okay, so that's kind of like how these 3 things relate for the same data. Cool, sound good so far? Awesome. All right, so now it's like, okay, this is cool. Like, I see how we can make the CDF. I see how we can make the PMF. The question you should ask me is like, how the heck do I make a PDF? Like, how do I create that, right? So that's what we're going to get into next, right? So we can actually visualize this into saying, well, how would you make this? So there's kind of two options. There's parametric fits and unparametric fits. So a parametric fit basically just means you're using parameters. You're using values to make your thing like this. So a parametric fit usually is like, we're going to make it into a normal curve. So essentially we give it the values of, well, how do we make a normal curve? We're going to put all the values in there and basically fit it close as possible. So we'll talk about that in a second in normal distribution here. But that's how we would do our parametric fit. Essentially, we'll take values from, we'll take statistics, I should say, like the mean, the standard deviation of your data, and put that into what this nice, beautiful mathematical object will be. Now, the problem with this, well, let me ask you guys, what's the problem with using a parametric fit if we're trying to make it this nice mathematical object, like this normal curve on this PD or PMF? What issues might you see already? Does that black line fit really well against the pink? Not really, right? Like, I mean, it's kind of got the general shape, but you can see like, you know, like maybe this is just by chance, like maybe it's like, oh, maybe this really is like a nice, you know, normal curve if it took many, many values. But there's a chance that maybe it's just like really spikes up in this area for some reason, right? And this PDF, this black line, doesn't really represent that value. So this is where unparametric fits happen. And so this is where we get something like the kernel density function, or, you know, kernel density estimation, okay? So KDE usually for what we'll talk about it. So you can imagine here is our histogram right here. And again, this isn't from my, this isn't from like my generated thing. I just want to make that clear. But you can see here is that these black lines, 1, 2, 3, 4, 5, 6, you can imagine those little black ticks right here are essentially the data itself. So you can see is that, for example, like this one's saying like, oh, that's like about like 2.5. This one's like, you know, maybe like, or negative 2.5 is like -2. This might be like -1, you know, something like that, or like -0.5. And then it's been together. So you can see this is probably how like real histograms would look like if you have a range, right? It's like, okay, there's only one that occurs within this range. There's only two that occurs in this range. There's only one that occurs in this range. There's nothing in this range, right? There's one in this range and one in this range. So the way we can basically build this kernel density function essentially is build little tiny distributions around each individual point. So I'm going to say, bear with me, because this is definitely where I think I lose a lot of people. But maybe quick, has anyone ever done, this is a long shot, has anyone ever done wave mechanics like in physics at all? Okay. All right, cool. I see a hand up. Oh, of course, the engineer, right? So if you guys remember back, like, I don't know, like in high school, if you did physics, or like even just playing around with like a jump rope, if you take like a jump rope and like you like move it up and down, you can make little waves, right? If you go on both sides of like each other and you do like a wave at the same time, and they come up, like and you imagine this little like wave pulse coming up, what happens when they meet? Does anyone know what they do? I like that explosion. They don't explode in that case. They actually add up. So like if they come across together and they actually add up, I guess that looks like what Strawberry's showing. They add up, and then when they pass by, they actually go back down. If you add a wave that's, I'm going to see if I can do this well with my hands. If you add a wave, like you go up on one end, and then your friend goes down one end, you can make a wave like going like this, and these two waves come across each other. What happens when they meet here? Does anyone know? Andy's got it, right? So they actually subtract together, and then they would like, you know, continue. My hands are getting a little crossed over, but they would continue on the other side. So that's kind of like what wave mechanics, and that's kind of like my best kind of analogy to what's going on here. So essentially we make little tiny Gaussians, little tiny normal curves on each part. And I'll explain why we do this in a second, but like essentially each normal curve, if you imagine, I guess I'll draw this, this might be easiest for you guys to see, is that if I draw this on here, so this is the data point, I draw a little, actually use my drawing tool, okay. Draw a little normal curve like this. And then draw a little normal curve for this data point here. Assume those all look the same. I'm really bad at drawing. But you can see if I draw each one of these on these normal curves right here, okay? I'm sorry, a normal curve on each data point, okay? And then what I do, I just add them up. So if I have a lot of peaks that are really close together, those will add up to a big peak. if I have only like, let's say a little peak right here, but most of them are very, very low, well, that peak's not going to get very high. It's going to be closer down here. So you can kind of see this general shape of like these are adding up together to make this big peak. This will basically be subtracted downward because this is all these like all these kind of like smaller waves. And then I have a big wave here. There's only a small moderate. It doesn't go down to 0, but just a little bump here. And then when I get closer to the side here, you can see these 2 points are larger. And this is more representative of our data, right? Where it's a little clustered right here. There's only 1 point right here, so it doesn't go to 0, but it's getting closer to 0. And then I have another bump right here, okay? And this is where we can kind of add these up together. Okay, does that make sense going from these little Gaussians to this big blue one right here? Okay, now the next question you really should ask is like, why are we using little Gaussians like to represent, this part? And the reasoning for this is that maybe this data point, even though I collected it and said, oh, this data point is value of 1, maybe there's some chance that I miss, like think of it this way, like human error, or like, my measurement tool wasn't quite off, or, like there's other parameter, like other dependent variables I wasn't measuring for that could make this value over here. But maybe if I did this value, if I measured that specific person over and over and over again, on average, they'd be right here. But sometimes they'd be a little bit off to the left, sometimes they'd be a little bit off to the right. Imagine if I'm measuring someone's weight. Let's say their weight kind of stays constant throughout the month, but it kind of fluctuates depending if I weigh them in the morning or in the afternoon, or maybe they had like a big, celebratory dinner or something like that. Or like they have been, doing really well, they have not been eating as much as they normally have because they're super busy or something like that. You might imagine this point being slightly off. So we modeled this basically saying, okay, let's pretend, essentially that's what we're doing here. Let's pretend we do this a bunch of times for each data point. And essentially we have the average, which is the actual data point we have. And then it kind of drops off saying like, well, there's a chance that maybe we could measure some off to the side. And that's where this Gaussian comes from to make the KDE. Okay, does that kind of make sense to people? Thumbs up if that sounds good. Sideways, you're like, eh. Okay, cool, awesome. I did an all right job, hopefully. Okay, but the point here is that we can make our nice thing, and this is not based on any parameters. We're not putting parameters in here. We're basically just taking this and using essentially the data itself to create this parametric fit, or not parametric fit, kernel density estimation. Okay, so you can see some this kind of what's it called, comparison, is that you can see here is that this green right here, this top one that kind of peeks out, that is a parametric fit. Basically, it's modeling like something like a Gaussian, right? So saying, oh, it should be a Gaussian, so I'm going to make it a Gaussian and essentially do this part. Where it's not realistic, the math is really nice on these Gaussians, but it's not exact, right? You can see there's a little bit of plateau going here, where the kernel density function basically will consider those little extra bulges and stuff like that. So this might be more realistic to the data, but it's a little bit harder to deal with like mathematically. So it's not as pretty and nice, but it's probably more truthful to the organic data. Okay, cool. All right, so I've been talking a lot about normal distribution, right? So let's talk about the normal distribution aspect. So normal distribution, like I'll call it normal distribution, Gaussian, bell curve. These are all the same things, more or less. Yeah, I would say they're interchangeable. Note that the reason why we talk about Gaussians and normal distribution is because they are just so beautifully nice, and they pop up out of everywhere. We'll talk about it. If you already talked about the central limit theorem, you'll see that they basically pop out from the central limit theorem. Essentially, things tend to follow a normal curve. And what's nice is that we really don't need very much to model them. And so this, you're going to say like, Victor, you're crazy because I don't know what you're talking about. Because this is the equation right here to model a Gaussian, which I don't know, if you look at this, I think it looks pretty, right? Like look how nice and beautiful that is. But the reason why it's so nice and beautiful here is that to make this nice bell curve, right, this nice normal curve, all we need is just two values essentially from the data. All we need is the mean, which is mu, this like kind of lowercase u, the Greek mu, and sigma right here, lowercase sigma, standard deviation. If we can calculate the mean, the standard deviation, we can make a Gaussian. And all the rest of this stuff, for example, you see the square root of 2 pi. What else we got? We got 2, we got e, right? So e is about 2.71, right? So Euler's number. So e to the power of this negative, x minus n. Essentially what we can do, we can determine for any given x on the x-axis, we can determine where this y part is, our estimated, what's it called? Our estimated frequency, right, which is y, by just putting in what the standard deviation is, what mu is, which is just the data overall, and then for whatever x we care about. So it makes it really easy for us to actually like formulate this. And this turns out to be actually very useful to find the area underneath the curve. Like basically calculus loves this number essentially, or like this form. So it's really easy to actually do calculations with. Okay, so that is the normal curve. And because of that, because it's nice, beautiful mathematics, we actually have very specific rules for it. So has anyone ever heard of the 68, 95, 99 rule? Okay, cool. I see a couple heads nods. So basically it's a shortcut so you don't have to do an integration and figure out what the exact area underneath the curve is. And essentially what it means is that with one standard deviation, and this is true for everything that's an actual normal curve, is that if you look at basically one standard deviation to the left, one standard deviation to the right, you basically get 68% of all the values in the whole distribution are within those 1 and 2 standard deviations. So if I were to color in this like 34, 34, this would be 68% of the value, or 60% of the values underneath here. It's about 68%. I want to make that really clear, but it's close enough for most things. And then if I went 1 standard deviation about from there, so 2 standard deviations from the mean and 2 standard deviations from the mean in this direction, that would encompass about 95% of all the data underneath. And then so 3 standard deviations, well, from the mean either direction, we actually get about 99.7. So about 99% of the data underneath here is underneath that curve within 3 standard deviations. So if you were like 3 standard deviations away from the mean, there's a very, very small chance that there's a very small chance for you being 3 standard deviations away from the mean, considering that the mean is true. Okay, so this actually would lead us into z-score, but I think I'm going to hold that off for a second before we do it. But one thing I did want to note is that basically you might hear, especially in the sciences, talk about standard deviations from the mean, and basically this relates into our z-score. But the likelihood of you landing over here, like past 3 standard deviations, is very, very small, right? So what happens, like if you imagine like giving a drug, like to like fix some like let's say heart disease or something like that, and see if it works or not like that. You can use it to say, okay, like, well, we expect them to be like 99% of the time within 3 standard deviations of having an effect. Well, if you're past that 3 part, it means that the drug might not have worked. Essentially, that's what our z-score or z-test will talk about. Now, this is the part where it's kind of interesting. It's like, okay, like what's that cutoff? In the medical field, basically about 3 standard deviations is considered like a pretty big result. I mean, like, whoa, like that's pretty significant. For other fields, it's a little bit different. Does anyone got a guess when, so anyone know what the Higgs boson is by chance, or have heard Higgs boson? It was discovered in the past like 10, it's got less than 10 years, like 7 years ago-ish. Like, I don't know, that's relatively recent in physics news. But the Higgs boson particle was discovered by, you know, particle physicists and stuff like this, and they had to make sure within certain standard deviations of how likely their thing was going to be a fluke. Like it was just by pure chance. So 3 standard deviations, like it's like, oh, that's amazing. We can give someone a drug to save their life. When they said that the Higgs boson might be there, that was 5 standard deviations, but they couldn't say that was not high enough for them to say, oh, for sure it's there. It wasn't until officially they hit 7 standard deviations, like, okay, now it's definitely, like we can say with certainty that's the true thing. And that's like a 99.999999, I don't know, % chance that it's actually the real thing versus like being a fluke, essentially. So just know different fields have different, you know, ways they measure of like how many standard deviations they're allowed. And this will tie again into our z-score that we'll talk about probably next time, because we'll talk about it again in t-score and everything. Okay, so I'm gonna skip over z-score for right now, but I will say, oh, is this it? No, that's not it. I'll skip over that. Forget it. I'll tell you z-score because we'll visit again. Our z-score, just to let you guys know, is basically just how many standard deviations from the mean you are. So if you are over here, okay, you do x minus mu and say divide by your standard deviation. That's how many standard deviations you are. If you have a z-score of 1, you have a standard deviation, or you are 1 standard deviation from the mean. If you have a z-score of 3.2, you are 3.2 standard deviations from the mean. That's all z-score really means, okay? And that'll be useful for us when we actually do our z-test, okay? So kind of to show you guys a little bit, if we have enough time, a little interactive graph, which I really like this, is that right here, ignore this one in green right here, but this middle one in gray, this is our normal curve, right? Our normal standard deviation, or our normal, our normal curve, our Gaussian, right? So you can see here is that that's what our nice things. And then what we can do here, we can actually adjust. Let's go standard deviation is just going to be 1. So let's see, 1. Okay, and then what this happens, what's it called? Mu itself, the average, basically is going off of that. So you can see here is that a standard deviation of 1, that is our normal curve, right? That is like the base. But if we had a mean of like 3, that just shifts the standard deviation or the normal curve off to the right, okay? And so we can see that we can adjust this. If we adjust the standard deviation, if the standard deviation is very, very big, that basically flattens out your normal curve, okay? And essentially it just means that when you have a larger standard deviation, that means that you're just likely to be further away from the mean. If we have a mean of, let's say 300 pounds for whatever thing we're measuring, right? So we're measuring like, I don't know, a bear, right? And the average is 300 pounds. If we change the standard deviation, right? And the standard deviation is like, oh, it varies by only, let's say like 10 pounds. That's a very skinny normal distribution, right? Essentially, the bears don't have much variety. But if the bears vary by like, let's say like 50, like standard deviation is like 50 pounds, well, that means basically it can be a lot of different possibilities. Like there's a lot of chance for it to be like 300, 350, 400, 450, versus if you only varied, our standard deviation was 10, it'd be very, very rare for a bear to actually have like a 450 pound bear. That's kind of outside of like really, really rare, okay? And so I just thought I'd show this little guy right here. You can adjust it. This green right here will be associated with like, basically like, what's it called? It's like area underneath the curve. So you can see like if I adjust this from 1 to let's say 4, you can see here, basically this will be about 68% underneath here. So if I show a probability calculation, you can see it's about 69%, right? Of the values are actually falling underneath here. If I adjusted to 2 standard deviations, right? You would see that's about 95, good, right? So our rules follows. And note that if I change the standard deviation now to make it twice as big, right? So now it's 2 standard deviations is our thing. You can see that 68 still, or sorry, our standard deviation is 2, twice as big. You can see that now going from 1 to about 5 will give basically 68% of the 68% of the values underneath there. Okay, makes sense. Okay. I thought this would be a nice kind of fun thing to kind of play around with, just to kind of see these different parts. And then of course you can see the z-score. This is x1, x2. You can see how many standard deviations are you away from the mean itself. So in this case, we're about almost, let's see here, 1 standard deviation. Oh no, sorry, yeah, 1 standard deviation because that's 2. So we're 1 standard deviation away, so it's about -1, and then 1 standard deviation this way, +1. If I adjust this now, this would be half a standard deviation, so about 0.4. Because I'm a little off on the numbers. Okay. Cool. All right, so I have that in there. Fun thing to play around with. And let's see here. We're going to say statistical testing for next time. But quick about deviations from the normal distribution. So not all things are normal, right? Our normal distribution by definition, the mean, the median, and the mode are all in the middle. We call this symmetric, right? Sometimes if you have a skewness, right? Positive skewness, negative skewness, that essentially has some values that are a little bit more on the extreme end. And essentially what happens, it brings out that mean. Because remember, the mean is not as robust, right, against outliers. So essentially if we add a couple outliers here, well, that will bring our parametric fit off to the side here and we'll have some skewness. So what will happen, we can kind of ignore the mode, but the median will kind of stay more or less the same, but the mean will kind of bring out forward. So we can actually say this has a skewness, and we say it's positive skewness. The skewness is about where like the tail gets pulled out to, if that makes sense. So that's like, we say this positive skewness or, skew to the right, negative skewness, skew to the left. Okay. There's a few ways we can like measure this numerically. I'm not going to go into it. The curriculum kind of talks about it, but essentially know that standard deviation, if you guys remember, here, I'm going to quickly just kind of write this down. Not real math in the sense of like what this actually represents, but if you imagine our mean basically is like some value, right? We're summing over some value divided by n. Our standard deviation, right? It looks something like adding up values, right? Squared divided by n. We can measure skewness as being essentially like how far, remember variance, right? This is really variance. Our variance, right, our standard deviation is saying how spread out are you from the mean? Well, you can kind of think of skewness as being like how spread out you are from the expectation of like the distribution. So what this will look like is that the calculation for this is actually something along the lines of the sum of everything cubed divided by n. So that kind of gives you an idea. It's like, okay, like you're basically encouraging things like really high values, extreme values are going to have a larger effect on it. The next part is kurtosis, and kurtosis basically is saying how spiky your distribution is. So imagine instead of like a distribution like this, you have a distribution that's still symmetric, it's not skewed, but it's like pointed outward like this. It's a lot skinnier. That would be high kurtosis. And this calculated for kurtosis, and got a chance of like what this would be in the sense of what power?
4.
Yeah, exactly, right? So that's the kind of like the reason why you would say, oh, this is where this value comes from. These values, people always ask me like, oh, what value is good kurtosis? What's value is a good like skewness? It depends on what you're looking at and stuff like that. Sometimes, usually we're fine with skewness if it's not too skewed. There's some ways you can kind of like say, oh, rule of thumb, but a lot of statistics is basically we get a number out, a summary statistic, and then we say, well, what does this mean anything? It's just a number essentially. So you need to decide what that number represents and like why that's important. Just to kind of show you kurtosis. Oh no, I don't have a description of that. So just kurtosis, essentially just know that's kind of like how skinny your distribution is. Okay. Yeah, any questions on that skewness or kurtosis? One ways to check this is usually visually, and then confirming it. Like if you had a specific, like you can look at numbers and stuff like that, but a number by itself means nothing. Even like we'll talk about statistical testing next time, using something called p-values and stuff like that. You need to know already that like, does anyone know by chance what the significance value that we usually use in pretty much all of science everywhere?
5%.
5%, 0.05. Yeah. It's kind of arbitrary. There's not a real like strong reason why 5%, like 5% or 0.5 is the right value. It's kind of arbitrary. It's a lot of ways. Some people have actually even talked about getting rid of significant values or changing significant values. Like maybe 0.05 is not good enough. For, like I said, for particle physics, 0.05 is not good enough. They actually adjust it to very much smaller level to make sure that it actually falls within what they're wanting. Okay, cool. But we'll talk about that next time. All right, cool. Any last questions before I end it here? Cool. All right, I'll stop the recording.